Hello all. In this video we will discuss about the Tsai-Hill and the Hoffman failure criteria, which are two criteria which are commonly used in the industry. So we'll start by looking at an outline. So we already discussed about the failure strengths and we also discussed about the biaxial failure criteria. In the previous video we looked at two failure criteria, which are the maximum stress and strain. But we said neither of them are matching with the experiments, and that's the reason why we want to focus on these Tsai-Hill and the Hoffman criterion. So let's start with the Tsai-Hill criterion. So Hill proposed yield criterion for orthotropic materials, and this yield criteria is an extension to the von Mises yield criteria. So this is the yield criteria proposed by Hill. As you can see, it has six constants: F, G, H, L, M, and N, which are again written. These are the failure strengths, written in terms of the fundamental failure strengths, again X, Y, and S. So mind you, here we are not differentiating between tension and compression. We'll talk in a while why we are simply writing it as X and Y instead of with the subscript. So now let's see if the loading is very simple, such that if only tau12 acts, which means that other than tau12 there is no other stresses, all other stresses go to 0. So when we substitute this in this yield equation, we get that 2n can be written as 1 by s square. So you can plug it and check it out. So because you will see that the only term which is remaining is this last term, and the rest all will go to 0, because starting from sigma 1, sigma 2, sigma 3 goes to 0, and the two other shear stresses go to 0. Okay. Similarly, if we apply again only sigma x acts or sigma 1 acts. In this scenario, again we will see we should be able to write it as g plus h is equal to 1 by x square. Now, if only sigma 2 acts, so then I should be able to write this as f plus h is equal to 1 by y square. And again, if only sigma 3 acts, now I should be able to write this as f plus g equals 1 by z square. So I need to mention what is z. Z is the failure strength in the third direction. Like y is the failure strength in direction y, and z is the failure strength along the third direction z. So since we are now looking at a three-dimensional stress state, we are looking at all three directions x, y, and z. Okay. Now let's try to simplify it. So we'll move from the three-dimensional stress state to the two-dimensional stress state. So let's say in 2D stress state, so we'll consider plane stress. So in the plane stress state, the stresses in the out of plane go to 0, which means sigma 3, tau 13, and tau 23, they all go to 0. So in addition to assuming it as plane stress, let's also assume that it is transversely isotropic. We can assume transversely isotropic in composites because earlier we have seen, like if we look at a cross section of a lamina, we see that there are several laminas, several fibers. So which means, and if this distribution of the fibers is random, then we said there is an isotropy in this plane, meaning in any direction the properties are the same. So what does this assumption of transversely isotropic help us? It helps us to show that any values in the direction y are also same as the values in z. So we can first show it with the strengths. So the strength in the direction y is same as the strength in the direction z. So when we make these simplifications where we moved from a three-dimensional problem to a two-dimensional problem, or we moved from 3D stress state to 2D stress state, and we also assume this transversely isotropic, then I can rewrite these yield criteria, which will be further simplified. So with these simplifications, now we are able to come up with an expression which is quite compact and simple. So in this expression, you can see we are now involving not just stresses along one direction, but instead we are able to write these in terms of the direction stresses sigma 1, sigma 2, and tau 1, 2. All these three components of the stresses are in one failure criteria, or the one failure criterion. Since we are able to write a single expression which involves the stresses sigma 1, sigma 2, and tau 1, 2, now we say that this is a failure criteria where there are interactions between the different stress components. Now let's apply this Tsai-Hill failure criteria to a uniaxial problem like we have done it for the other two failure criterions. So here is the lamina where we apply the stresses along the x direction, and here are the fibers at an angle theta. Okay. And then we should be able to rewrite that expression using the stress transformation. So previously we showed the stress transformations as sigma 1 is sigma x cos square theta, sigma 2 is sigma x sin square theta, and tau 1 2 is minus sigma x sin theta cos theta. If we plug in these expressions in the earlier expression, now we should be able to rewrite it as, so this is the modified expression after we substitute these stresses in terms of the applied load sigma x. Again, we see that here we have an interaction between the three strengths x, y, and s. Okay. So earlier I was mentioning that why we don't have a subscript. So now is the time to discuss about it, because now what we'll see is in each of the coordinates. So meaning like once we find these sigma 1 and sigma 2, if both of them are positive, then we replace x with xt and y with yt. So let's say in the first quadrant we use xt and yt. Similarly in the third quadrant we use xc and yc because both sigma 1 and sigma 2 are negative. But in the second quadrant we use xc because sigma 1 is negative, and we use yt because the sigma 2 is positive. And similarly in the fourth quadrant we use uh, xt and yc. So whether to use tension values or compression values will depend on the sign of sigma 1 and sigma 2, which means this expression keeps changing from one quadrant to other quadrant. So there are some salient points to be noted when we discuss about this Tsai-Hill, that it is a continuous smooth curve in each quadrant. But the place where it moves from one quadrant to the other, though it is continuous, the slope may not be the same. At intersections, it is continuous but with different slopes. And more importantly, when this failure criteria was compared with the experiments, the agreement is good. And we already showed in the previous slide saying that now we see an interactions between the different failure strengths. So like x, y, and s, we are able to bring all these different failure strengths into the single expression. That is why we got a continuous smooth curve at least in each quadrant, because moving from one coordinate quadrant to the other, we said we need to take care whether it is a positive or negative. Accordingly, we will give a tensile strength or a compressive strength. Now, this is a time for us to compare how the Tsai-Hill compares with the maximum stress and the maximum strain failure criteria. So we'll do it in two ways. First, we'll look at the plot which we already showed for maximum stress. So when we discussed about maximum stress failure criterion, we said if we are plotting with respect to theta going from 0 to 90, and again if we are focusing on these uniaxial tests that we are discussing, we said because of this uniaxial test in tension, both along the fibers and perpendicular to the fibers, you have tension. So you have one criteria coming from along the fibers, which is dictated by xt, and the other coming from yt, which is coming perpendicular to the fibers. And then there is, because of shear, we had one more failure criteria, but we said design will be with the least strength. So we said this is the failure curve we need to focus on. This is for maximum stress. Though we didn't discuss there, but even if we write it for maximum strain, the curves are not the same but similar, meaning that you need to apply again different criteria for whether along the fiber, perpendicular to the fiber, or shear, and then depending on that you will get a failure curve which is again a mixture of three curves. So this is for both maximum stress and maximum strain. Of course, both are not the same because these values will slightly change, and we already mentioned that the Poisson ratio nu1 2 and nu21 also come into the expression when we discuss about maximum strain. But the similar thing, if we do it for Tsai-Hill, usually we, at least in one quadrant. So for example, in these uniaxial loads, we said sigma 1 is positive, so we apply tension, sigma 2 is also positive. So in this case, the Tsai-Hill will be a continuous curve, something like this. So it is a curve going from theta is equal to 0 to 90, how the failure strength sigma x varies. Okay. So the salient point, as we already mentioned, is one, it is smooth. We don't have cusps like what we have seen in these maximum stress and maximum strain. And second, we said we are able to bring in the interactions. Okay. So there is another way to compare these three failure criteria. Here, let's plot it in terms of sigma 1 and sigma 2. What are sigma 1 and sigma 2? These are the stresses along the fibers and perpendicular to the fibers. Let's say the stress rate is something like this, where we are applying sigma 1 and sigma 2, and these are the fibers. So along the fibers is sigma 1 and perpendicular to it is sigma 2. So in this, we need to take care of one thing. We know that the strengths depend on whether it is tension or compression. So along the fibers, we know the strength along tension is higher compared to compression in most materials. Maybe there are some materials this might change. But perpendicular, again, let's say in compression it is high than this. So mind you, here we are for now assuming that there are no shear stresses, but of course this theory can take care of shear as well. But we are not looking at a special case where tau on 2 is 0. So it's only a special case, it's not the complete thing we are showing. So in this special case, how will we show the maximum stress? It will be like a rectangle, something like that. Now let's show how the uh, maximum strain looks like. Maximum strain, the lines are not neither horizontal nor vertical. The reason is because of the Poisson ratio, there is an inclination. Let's try to capture that inclination here. Okay. So the slopes here can be shown with nu 21 and the slopes here can be shown with uh, nu 1. Okay. So this is the maximum strain. So here we can also show the Tsai-Hill, but as we already know, Tsai-Hill should be drawn one quadrant at a time, because in each quadrant your choice of xt versus xc comes in, or versus the yc comes in. In the first quadrant we do it based on yt and uh, yt and xt. So let's say quadrant is something like this, and let's say in the third quadrant again it is another curve, and these are the each curves in each quadrant. So we are saying this as the psi. So as we showed, in each quadrant it is a smooth curve, but at these intersection points, though it is continuous, the slope can be different because it is now dictated by a different equation. These are not the same equation to give the similar slope at the intersection points. So this should give a brief comparison between the different failure criteria we are using. So the maximum stress and the strain, we see that there are curves, but when we move to the Tsai-Hill, we have shown that it is a smooth curve. And in this here we see that in each quadrant it is smooth, but at the intersections there is a change in the slope. So with this, let's now move on into the last failure criteria, which is the Hoffman. Okay. So in the Hoffman failure criteria, we try to address one disadvantage with the Tsai-Hill, where we said you need to deal with four different curves in each of the for the four quadrants. but that can be avoided by adding linear terms to the yield criteria. That's what Hoffman suggested. So Hoffman added linear terms to account for different strengths. So according to him, the expression is written in terms of. So as you can see, there are 9 constants, C1 to C9. This will be related to the 9 strengths. What are the 9 strengths? These are XT, XC, YT, YC, ZT, ZC, and similarly shear strengths S23, S31, and S1. So we have 9 unknowns in this expression, C1 to C9, which are related with the 9 strengths. Since we are now looking at a 3D stress state, but now let's simplify and move from the 3D stress state to the 2D stress state. That we can do by assuming plane stress. So now let's say we are only focusing on plane stress, sigma 3, tau 1 3, and tau 2 3, all of them going to 0. And we will also assume transversely isotropic. Like we showed earlier, it is in transversely isotropic, since the directions 2 and 3, the plane of 2 and 3 will have properties the same in all directions. We can now write that as yt equals zt and yc equals zc, meaning the tensile strength in directions 2 and 3 are the same, and compression strength in directions 2 and 3 are the same. So once we make these simplifications where we move from a 3D state to the 2D state with the assumption of plane stress, and then we also assume transversely isotropic because most lamina can be assumed this fashion. Then we can simplify the expression suggested by Hoffman as this is the expression written for the 2D stress state for a transversely isotropic material, where we have written in terms of these components sigma 1, sigma 2, and tau 1. So the interesting fact about this equation is now we are able to, in a single expression, combine the strengths both in tension and compression along the fibers and perpendicular to the fibers, as well as the shear strength S. So which means with one single equation you can just look not in a single quadrant but at all 4 quadrants. So this is a very added advantage with the Hoffman failure criteria, because it is now very easy to implement. One need not really look at whether your sigma 1 and sigma 2 are positive or negative values. No matter what, you can simply plug in this equation and it will give you an effective whether the composite is safe or will it fail. So now let's look at some salient points about this Tsai-Hill. First, when compared with the experiments, it showed that a good agreement is shown with the experiments. Second, it also showed that single curve can be used in all quadrants. Though I mentioned its quadrant as though it is just in 2D, but even if you go to 3D, basically for any stress state you use the single curve, and we show that there is an interaction between different strengths. And lastly, we know that it is simple to implement. Of- And for all these reasons, Hoffman criteria is very commonly used in the composite literature. Now let's summarize what we have discussed about the failure of a lamina. So we have looked at four different failure criterions. We started with the stress and strain, where there are no interactions between different strengths. But later we looked into Tsai-Hill and the Hoffman and showed that there are interactions for different strengths in the material. So the difference between Tsai-Hill and Hoffman, we showed that Tsai-Hill is good for each quadrant you have a smooth curve, but going from one quadrant to the other quadrant you will have a different curve. So one needs to take care of changing the equations of the curve going from one quadrant to the other. But Hoffman criteria is able to bring in both the tension and the compressions into a single equation, thereby trying to connect all the strengths using one single expression. So this becomes easy for a designer to apply to see whether this composite is failing or whether if it is safe. So this should summarize what we have discussed about the different failure criteria of the lamina. So with this we'll conclude this topic, and in the next videos we will now move from macro mechanics to the micro mechanics. Until now we have been only discussing about the macro mechanics, meaning that we are assuming this lamina as a homogeneous material, though we know it's composed of fibers and matrix. But in the coming videos we'll see, if we know the properties of fibers as well as the properties of the matrix material, how can I use that or start from there to predict the properties of the lamina? See you then.